was correct. Convex sets, again this turned out to be different, right. So, we will only describe a subset of these. Okay. So, a special what has happened to my spelling skills? Polytope and polygons, right. And this is going to be your not just for the standard ones, right. This is going to be intersection of your constraints. Okay. And let us look at this. So, let us make this picture complete. This was a affine set or a hyperplane. Geometrically, it was a hyperplane. It looks like a plane moved from the origin to some other place. Fine. What is this? Yeah, this is not a plane, this is a half plane. We call it half space. And yes, you take a line, this is the line describing A transpose X equal to B, either this side or that side, depends on what A and B are. One part of this is going to be A transpose X greater than equal to B, other is less than equal to B. Cool. Okay. And now, if I take intersection of half spaces, I start getting polygons. How do I get it? I need more colors. This is an inequality. This is an equality. This is an equality. This is an equality, right? If I take the intersection, I get this polygon. Okay, but now you also see that it need not be bounded, right? For example, if I take intersection of this is a convex thing, but it is not bounded, but whatever boundaries are there, they are lines. This is a polygon, this is a polytope, this is also a polytope, but this is also a polygon, right? Clear? So, this is what we achieve with this intersection of A transpose X, intersection of A transpose X less than equal to B. So, now I can give you a mathematical definition of a polytope, which is a set S which is described by some inequalities So, any set which is kind of intersection of our constraints is going to be a polytope. And to prove that this is same as the geometric picture is called Minkowski-Weyl theorem, and we are not going to worry about it. We just thank Minkowski and Weyl that they proved it. It's going to be very useful, but kind of not that easy to prove. So you will skip it. But what we will remember is this dual picture. Oh, this is saying that these two definitions are the same. So okay, I have to be much more careful. This is going to be a polytope. This is how I define a polytope. This is going to be a convex hull of finite number of points with some rays. Like you have this infinite directions, right? So then you have to precisely define this, but I want to just do it geometrically. But there is a kind of a cleaner way that you have finite points and then you have convex hull of that, and you're allowed to extend them in lines, and that is going to be your polytope or polygon, and that is same as these equation description. Okay. Yes. Yeah, in 2 dimensions hard to visualize, but if you take them in higher dimension, you will see that they will give you some kind of. So it's easy to see that these intersections will be convex, right? And then their boundaries would be linear. So, and yeah, but I cannot draw 4 dimension, and I cannot imagine also, visualize also. So even when I say that these intersections are going to be convex set, polygon or polytope, I believe Minkowski and Weyl, right? So they look something like that. But yeah, I understand it's weird because this looks like a linear subspace, but then we are taking intersection, so that linear subspace will be cut into parts. Okay, but the whole thing was done so that we understand convex sets are feasible region nicely. This is feasible region. So our feasible region is going to be polytope or polygon.
So why is the theorem not valid?
No. This theorem is telling us that our feasible region will look something like this. But where did you prove that this set looks like, or let's say if it is bounded, it's a convex hull of finite number of points. What are those points?
How do you exactly define a polytope?
Mathematically, 2 ways. This is one, and other, as I was pointing out to him, you say you take few points and few directions. Okay, so it is convex combination of points, and then you can extend them in any direction. But that is not going to be useful. That's why I am not doing it. You can read about that on internet, but it is so. If it is finite, if it is bounded, then it is clearly convex combination of finite sets. But now we want to allow infinite rays also. So it is convex combination of points, and then you can extend them with some rays. So there are vertices and then there are rays. That is how you can define them geometrically. I am just giving you a picture for that. Is that okay? So yeah, x1 to xn, v1 to vk, then it is convex combination of this plus, I haven't defined cones for you yet, but you can extend them in this direction, v1 to vk. Here there is no the coefficients of this need not sum up to 1. Just go in that direction as much as you like. Okay. So for example, if you remember this, it is convex combination of this extended in this direction. There is one direction where it can lead to. Okay. This is the picture we will have in mind. The thing which we have not talked about is cones.
So you said special kinds of convex sets are polytopes and polygons.
Yes.
So then what excludes polytopes and polygons in convex sets?
Circle. That's why I draw those weird shapes which looked like convex, but you were not sure. All those shapes are. Sorry? No, this extension is also there, right? So that's why if you want to be mathematically precise, then you have to appeal to this Minkowski Weyl theorem. Okay. So we have seen affine combinations, we have seen convex combinations, and then the thing which is left is what we call conic combinations, right? And your question should be that, oh, we defined affine, we defined convex sets, what about conic sets or something? First, I define cone, a set S is called a cone if for any point x, this is the line from origin to alpha is contained in S. Okay? So it basically looks like a cone. It's a cone if it looks like a cone. Okay? And now you might be asking, what if, is it true that if I take 2 points, their conic combination is inside the cone or not? What do you think? Yeah. Oh, sorry. Yeah. Thank you. Thank you. Oh, half line. Yes. So what do you think? Does the cone contain all possible conic combinations of the points inside it? That's because you don't use pen and paper. Just these 2 lines. Is that a core or not? Yeah, this is origin, yes. But it definitely doesn't contain the conic combination of these 2 points. Right? So, yeah, there are reasons why we study cones, and then we study convex cones, which are going to be, more like containing all the possible convex combinations also, but that's for the next class. Okay? So now our plan is learn about convex cones, then convex functions, and once we learn that, a nice algorithm for linear programming will pop up. And you might think, oh, we did all this linear algebra and our efforts went to waste. No. The things which you learned, remember the solution space looks like this, all that intuition will be helpful while implementing solution based on this. Okay? This is a good reminder, nothing goes to waste, especially in math. Right? So we did linear algebra, it did not give us, it gave us simple solution, but now we will see with this extra conditions, our solution becomes slightly difficult, but that can be obtained from what we have seen by modifying them appropriately. Okay? And that's the plan for future lectures. Thank you.